Okay, hi everyone again. In this video, I want to talk about and show you two examples of specific energy diagram. Uh, so we already discussed the specific energy definition and a specific energy diagram and how we can draw it. And now we want to solve an example for that. So specifically for the first problem, wants us to determine the depths of the water, or Y2, or elevation of the water surface downstream of the ramp, right? So actually we want to find what is Y2 or Y2 plus Z2. Z2 is given in the problem. So this is the problem configuration. The Q is given for us, so it's 5.75 foot square over second. We neglect all the viscous effects, so the friction or friction slope is 0. And V at the entrance is 2.5 foot per second. Z at the beginning this section, Z1 is 0. And then Z at the section 2 is 0.5 foot. We don't know the V2, we don't know Y2, and we know that the width of this channel is constant. So we have a constant width channel. So our unknown is Y2. We want to see what is Y2 and the depth of the fluid in section 2. Okay. So let's start writing the energy equation. So S naught L in our S0L or S naught L in our problem is going to be Z1 minus Z2, in which here, and also we have the HL equals to 0 because we don't have any viscous effects. So we can just plug these into our specific energy equation, or even energy equation, which is going to give us this value. So it's going to, we have Y1 plus V1 square over 2G plus Z1 equals to Y2 plus V2 square over 2G plus Z2. So Z1 is 0, Z2 is 0.5 foot, Y1 is given in the problem is 2.3 foot, and V1 I can calculate it based on the value of Y1 and Q, which is going to give me Q over Y1 is going to be 2.5 foot per second. Okay, so these all are going to give me the energy equation here. So the energy equation is going to be 1.9 equals to Y2 plus V2 square. So because 2.3 minus 0.5 is going to be 1.9 equals Y2 plus V2 square, V2 square over 2 times, and also I have calculated this V1 square over 2G. So all these three are gonna be 1.9 equals to Y2 plus V2 square over 2 times 32.2, which is G in British units. Okay. So this is gonna be my equation 1, which is coming from the energy equation. And then I want to find Y2, so I have two unknowns, Y2 and V2, so I need another equation. So I write the continuity equation. So continuity tells me that Y1 times V1 should equal to Y2 times V2. So this means that Y2 V2 should equal to 2.3 times 2.5, which is going to be 5.75 foot square per second. Okay, so this is the second equation that comes from continuity. And now I combine equation 1 and 2 together, and I get to this cubic equation for Y2. So I combine these. So instead of V2 here, I'm gonna write 5.75 over Y2, and then Y2. So and then multiply everything by Y2 square. So I'm gonna get Y2 cube. So I combine these two and then multiply it by y2 square, I'm gonna get this cubic equation based on y2. So I'm gonna get y2 cubed minus 1.9 y2 square plus these values. If you just calculate it, it's gonna be 0.513. So this is gonna give me, combining these two equations and multiplying by y2 square is gonna give me this equation. Okay, so this is a cubic equation, and then I want to solve these to find the roots which are gonna correspond to this y2 here. So there are multiple ways to do that. One way is you can use trial and error. So you just guess some values, like you just guess this here is 2.3, so you can just guess like 1.5 or 2 and then put it here and see whether you converge or not. And the other way is you can put this in a calculator, and calculators also give you the roots for this equation. And also there are some analytical ways you can find the roots of these equations. So if you find the roots of this equation, you will find three roots. The first one is y2 is 1.72 foot. Second one is y2 equals to 0.6380 foot. And then the third one is a negative value minus 0.466 foot. So as you know, we cannot have a negative y2, right? It has to go below the ground, which doesn't make sense. It's not physical, so we just neglect this root, and we are only left with these two roots. So we can have two possibilities. And now we want to see which of these are correct, which of these are the correct y2 value in our problem. So here we have y2, it's either this one or this one. So let's see which one is correct, which one is expected. So we have y2 plus z2 is going to either give me 1.72 plus 0.5 foot, which is the z2 value, is going to give me 2.22 foot, or y2 plus z2 is going to give me 0.638 plus 0.5 is going to give me 1.14 foot. So one of these values is correct, and let's see which one is expected. So in order to find which value is expected, we can use energy diagram. Okay, so energy diagram is useful for here. So in the energy diagram, specific energy diagram, we have E equals to y plus q square over 2gy square. So I write it y plus 0.50. So we have the value of q in our problem. So the q is 5.75, which is given. And you also know 2g, which is 2 times 32.2. So I just calculate that number, and it's going to give me this 0.513 over y square. And for E1, I know that because I know the depth, which is 2.3. Again, is given here. So at section 1, the energy diagram is going to give me 2.4 foot. Okay, E1 is going to be 2.4. And then the next thing I want to find in order to draw the energy diagram is the minimum energy or critical energy. So it's going to be 3yc over 2. And what is yc? Yc, we found the formula for that is going to be q squared over g to the power 1/3. So if you calculate these and plug all these numbers, so q we have 5.75 over g 32.2 to power 1/3, you're going to get 1.01. So I just plug in it here, and then I'm going to get 3 times, so I'm going to get 3 times 1.01 over half is going to give me 1.71 foot. So this is going to be the minimum energy level for this specific Q, for this Q, I'm gonna have the minimum energy level for me is specific energy is gonna be 1.51. And YC, the critical Y, in which the Freud number is gonna be 1, is 1.01. So now that we have all this information, we can draw the energy diagram, a specific energy diagram. So Y equals to E line, you first draw that, and then at the Y goes to infinity, your line goes around there. Then you have the minimum energy level. So the minimum YC, the critical YC is 1.01. So I just draw it here. The minimum E is going to be 3/2 of that. So it's going to be 1.51. So I have it here. So I have this point. And then the point 1 is energy at section 1. So Y1 is 2.3. I have it from the problem statement, and E1 is going to be 2.4. So I have this point as well. So now I draw this specific energy diagram, and then I want to find E2. Okay. So E2 here we can see what's going to be E2. So from the energy equation, we have this E1 equals to E2 plus SF minus SL, SFL minus SF S not L. So SF is 0, so I just neglect that term. Okay. And then I have E2 is I'm gonna get E2 minus S naught times L. So I'm gonna S naught times L is Z2 minus Z1. So Z2 minus Z1 is 0.5 from again the problem statement. So I'm gonna get E1 equals to E2 plus 0.5 food. Okay, so E2 should be E1 minus 0.5, which is 1.9. Okay. So I just draw this. I just draw this line. E2 equals to 1.9 foot. I go up, and then as you see, I have two roots. These two roots are shown as this cross here, as this signs here, as these symbols here. So these are actually my two roots, right? So the first one is gonna be 1.72 foot. And then the second one is going to be 0.6038, okay, 638, okay. So as you see, this one is in the supercritical regime, and this one is in a subcritical regime. So here Freud number is 1, and here we are in a deep channel with slowly moving fluid, so we are in a subcritical regime, and here we are in a supercritical regime in which we have a high-speed flow with shallow channel. Okay. So we have scenario 2 and scenario 2 prime. So for scenario 2 prime, in order to for it to occur, okay, the flow should move from 1. So because we are having a constant Q value in our problem, right? So in our problem, as you can see, this Q is given. So we are only moving to through this Q. So in this diagram, so we have to go from point 1, and then we have to go to point 2. We have to go to this point, E mean and YC, the minimum energy level. So our Freud number should go to 1, and then finally we go to from here we go to the scenario 2 prime, right? So as you see here, before Y goes to 0.6038, Y has to go to a critical value, which is 1.01. Okay, so before going here, Y has to go to 1.01, which is a critical Y value. But as you see here, E1 minus E min is gonna be 2.4 minus 1.51, so is gonna equals to 0.89 foot, which equals to the Z at critical, Z critical minus Z1. So we have to have a 0.89 foot change in the elevation in our problem in order for the flow to go from scenario 1 to critical value, its minimum energy level. So we have to go like, if it is here, so like if it is 0.5, you have to go somewhere around here before reaching here, right? So we should have something like this. So we should have a bump here. We should have a bump here, and in order to, and this value is based on what we found is 0.89 foot, right? So we have to go from here to here. So then here we are going to have a critical value, a critical depth, and then after that we can go to this regime, to this supercritical regime, okay? However, as you see, we don't have that elevation change in our problem, right? So because we don't have that elevation change, then scenario 2 prime is not going to happen, right? In this problem, scenario 2 prime is not feasible, so only scenario 2 is feasible, right? So we can go from 1 to 2, very small change, and it's feasible here, right? So we have this movement from section 1 or energy level 1 to energy level 2. So the correct answer for us is gonna be this answer, right? So this is the right answer, and this is not feasible, okay? So Y2 plus Z2 is gonna be 2.22 foot, and Y2 is 1.72. So this is the water surface elevation, free water surface elevation in section 2 for us. And the elevation of this free surface, we can calculate that, is going to decrease 2.3 minus 2.22 is going to decrease 0.07 foot. So actually here, as you see, Y2 plus Z2 is going to be 2.22 foot. So here, elevation is going to decrease a little bit. It's going to decrease to 0.0. It's going to decrease about 0.07 foot. Okay, so this is how we use a specific energy diagram to find the water elevation and water surfaces, free water surfaces in hydraulic problems. Okay, so now I want to solve a second example for a specific energy diagram. And in particular, I want to talk about triangular channels. So these are a little bit different than rectangular channels that we have talked about so far, but there are not much differences because the governing equations are again the same. I just want to show an example to you, so if you see that later on, you know how to work with this kind of problems. So we have a triangular channel in which we know the angle between these two, which is 100 degrees. And we want to calculate the critical depth and velocity for this channel, which has a flow rate of Q equals to 16 meter cube per second. Okay. So let's see what is the critical depth and velocity. So as you remember, this is the specific energy equals to Y plus V squared over 2G, and instead of V, right, instead of V I can write as Q over A, which is the flow rate, over A. So this is gonna give me this y plus q square over 2ga square. And we know the critical depth occurs when for the minimum E, and we can find the minimum of E by setting dE over dy equals to 0. Okay. So first let's see what is gonna be A here in terms of the channel height. If we assume this is the y, this is the depth of the channel. So here I can say that based on this is 100, so this angle is gonna be 50 degrees. So B, the width of the channel here, over y is gonna be tangent of 50, right? It's gonna be tangent of 50. And the area here is gonna be B times the area of this rectangle. This is gonna be B times y over 2, right? So it's gonna be 1/2 y times tangent of, instead of B, I'm gonna write y times tangent of 50. So this is just B, which comes from here. So y times tangent of 50 times y is gonna give me y squared tangent of 50 degrees over 2. And then I have two of these triangles. So I just multiplied it by 2 to get the whole area of this cross section. So it's gonna give me 2 times by over 2 is gonna be y squared tangent of 50. So this is gonna be the area of the channel in terms of the depths of the fluid, or y here, okay? Because we don't have a rectangular channel, it's gonna be something like this. Okay, so now that we had this, we can now find put this into the energy equation, and then take the first derivative to find the critical depth. Okay, so the specific energy is going to be y plus q squared over 2g times what? A is y squared tangent 50, and we have a squared, so it's going to be y to the power 4 tangent square of 50. So I can write this, the whole thing, as a like a constant c, because q is given in our problem, which is 16, and 2g is also, we know it's a gravitational acceleration. Tangent 50 is constant, so everything except y to the power 4 is constant. So I can write this as a constant c times y to the minus 4, and then take the derivative to make it easier. Okay, so d over dy, so the first term is gonna be y is gonna be 1, because I'm taking the derivative with respect to 1, and the derivative of y with respect to y is gonna be 1, and then minus 4. So here the derivative of minus y to the minus 4 is gonna be minus 4 times y to the minus 5. Okay, so, and then I have also c here, so I just write it down, and this should equal to 0, and then I will get the critical depth. Okay, so based on this equation, I can get the critical depth yc should be 4c to the power 1 over 5. So let's see what is c. So c is q squared over 2g times tangent square of 50. So it's going to be 16, which is given in the problem, times 16 over 2 times 9.81 times tangent square of 50. So it's going to be 256 over 27.86, and it's going to give me 9.2. So I can just plug this into here and then find YC. So I am going to get YC equals to 2.06. So the critical depth is 2.06 for this channel. So if the Y is 2.06, the Froude number for this channel is gonna be 1 for this given flow rate, okay, for this particular configuration. And what's the critical velocity? The critical velocity is gonna be Q over AC. So Q is 16, and AC, the critical area, is YC square times tangent 50. So YC square, I have YC 2.06, I just plug it here, and tangent 50 I calculate, and this is gonna give me the critical velocity. So the critical velocity is gonna be 3.16 for this channel. And the minimum energy level for this channel that can have occur, the minimum specific energy is gonna be 2.06 plus VC square over 2G. So I have VC here, square over 2G, is gonna give me 2.57. So these are the two values that the problem wants from us. The critical depth is gonna be 2.06 meter, which is the depth in which for this particular given flow rate, the channel is gonna be in critical Froude number, which is Froude number equals to 1, and the critical velocity is going to be 3.16 meter per second. Okay, so this is the end of this specific energy diagram discussion, and in the next session we are going to talk about the uniform flow Manning and Chezy equation. Thank you very much, everyone.